recording. All right, so let's download the lab, get through it. Actually, yeah, let's do that. There is this test review that I want to go through too. Okay, so it's a two-part lab. And the first part is going to be model calibration, but I'm just going to, let's just do this part kind of together. That's the, oh wait, no, not that part. This part, the part 2 regression. And then that'll help talk about regression a little bit more. Okay. So I'm going to go ahead and open up ArcGIS Pro. Make a map. This is regression. I got to download the data too here.
Did you restart recording?
I did. Yep. I started recording. So hopefully it's still processing the earlier one. So that's good. I hope it's good. Oh no, wait, that's this one. Yeah, the 59-minute one. Yeah. I wonder if I can play that one while we're. Looks like it worked. A numerical map. Yep. That guy sounds like a nerd. All right. Yeah, you always sound horrible when you're. At least I do. I hate the sound of your recorded voice, but really that's what everybody else hears, which is kind of discouraging. All right. So. All right, I downloaded the data, and I'm going to go in there. There's two different GDBs, two different file geodatabases, and I'm going to copy those. I'm just going to put them in ctemp, SA, make a new folder called Lab 10, and put both of those in there. Oh, they're kind of big, I guess. Oh, it's doing it though. All right, for the regression one, we're going to go with the USA data, usadata.gdb. So I'm going to bring that data into ArcMap. So, I mean not ArcMap, ArcGIS Pro. So that was in C, SA, SA, Lab 10, USA data, and then I'm just going to add it all. Control A, adding it all in. While that's adding in, I'm going to talk about it for a second. So what we're going to do is we're going to calculate lapse rate. Lapse rate is defined as the rate of decrease with height for an atmospheric variable. In other words, as we go up in elevation, how does temperature change? So we're going to use temperature because that's the most common lapse rate that's calculated. So you should maybe have learned in another class, or maybe not. But as you go up higher, it gets colder in general. That's dependent on lots of things. One of the major things that it's dependent on is the humidity. So it changes changes in different areas. In an area that's not very humid, you can go up higher and you get a lot colder. So we're going to be calculating lapse rate. So using regression, we're going to calculate the lapse rate. So the first step will be to transform the climate variable you have in a given data set so that they are summarized by county. We could do this on a cell-by-cell basis, but it takes a lot longer. So we're going to do it by county. So what operation do you need to use to transform raster data and get a table that summarizes raster value by a zone? There we go. So we don't really need these large cities. That's kind of interesting, but not really. Those are the counties. So what we want to find out what the temperature is. What the temperature is what the average temperature is in every single one of these counties. And we want to know what the average summer temperature is, the average winter temperature, and we want to know what the predominant land cover is, and the average elevation for every single one of these counties. How do we do that? Let's just think of it one at a time. How do we find the average winter temperature by county using a tool in GIS? Yeah, they should know that my favorite tool is zonal statistics by now, right? Is your sound turned off down there? Oh, okay. Yeah, zonal statistics, and in this case, we're going to get zonal statistics as table. So we're going to be able to throw in, for our zones, we're going to throw in our counties. And the zone field is going to be, well, we can do whatever we want. We want to be able to join it back in later. And so you need to pick something that's unique. So let's actually look at the counties table. We could actually use the one called name. Do you know why that's not a good one to choose? Yes, I grew up in Orange County. I wonder how many Orange counties there are. You guys know? Right? I was born in Orange. I mean, not born. I was actually born in LA County, but I grew up in Orange County, California. OMNOP. Man, there's lots of counties in this here country. Look at that. 1, 2, 3, 4, 5, 6, 7, 8. Orange County, Vermont. They don't grow oranges in Vermont. New York, Indiana, Virginia, North Carolina, California, Texas, and Florida. That's a lot of orange counties. So yeah, we can't use name. So yeah, you got to choose. We got object ID _1, and I'm not really sure why there's 2 object IDs. Probably because it was derived from another data set that already had a field called object ID. But my guess is either of these 2 values is unique. So I'm going to choose object ID number _1. You just have to remember which one you chose. Actually, let's choose this one because it's easier. So the value raster is the raster that we're trying to derive the value that we're trying to get the value from. So that would be, let's start with winter temperature. So we got winter temperature, and then we're going to call this winter temp these. And we're really only concerned with, what was it? The average windage temperature. So let's just get the mean. So I got that all set up like that. Counties, object ID, average windage temperature. I'm going to call it winter temperature counties, and then mean. I'm going to run that guy. And what's going to happen is that now I'm going to have a data set. Here it is. I'm going to open that up. And these values represent the mean, the mean temperature in that county, well, one of the I'll have to figure out later which one these have been. Look at that. The average winter temperature is negative 137.91. Is that real? I wonder what county that is. So how would we find out what county this is? For those of you taking an intro to GIS class, how do I find out how do I make a map of all these counties? How do I go back? What should I do? I already used the word. I tell you what, I got a table, and it needs to be connected to a feature class or a shapefile. What should I do? Yeah, exactly. So what I can do to get this back into this table is go under the counties, right-click, and say joins and relates, add join. What that's going to do is create a virtual a connection between these two data sets. So I've got my counties, and I want to join the mean field. What's it saying there? Field mean does not exist within the table. Oh, that's right. I don't want to join the mean field. You're joining on the field that that has a common value. So I'm going to join on object ID because that's what I told it to use, and I'm going to join the what did I call that table? Winter temp counties. And then I'm going to join on object ID. So I'm going to run this guy. You know what? I actually think that it's doing some weird thing here. So this object ID _1, I do think I want to use that value. Okay, the reason why is I think that it's creating this automatically, and it's grabbing this object ID _1 as the field I told it to put into the table. Anyway, that might be a little bit confusing, but I'm almost positive I'm correct. It's confusing to me too, but all right. So it's joined it now. Now if I open up this table, I've got a field called mean right here. I can make a map of it.
What did you do differently right there? I'm sorry.
What did I do differently where?
You joined it again, is that right?
No, I didn't. I only pressed run once.
See, I pressed it and then tried again.
Oh.
Yeah, if you do the original.
So you right click on counties and you could say joins and relates, remove all joins, and then it'll remove it. Then you can run it again. And it'll join it back up. All right, so then if we click on the symbology here, now we can see this. Oops. I want to go graduated colors.
And real quick, you said you just used the object ID for both fields?
No, I did that at first, but then I used object ID _1 for the second one.
Gotcha. Okay.
Now this actually kind of looks reasonable, right? Like this map right here, but this I'm actually mapping object ID, not temperature. So here's the mean temperature by county. Let's do like hot to cold. Got any red ones? I don't know, I think they took out like some of the schemes.
It almost seems like different schemes appear with different metrics or.
So you can change it here. You can say, okay, I want to go from red. Actually, I want to go from blue, meaning the cold places, the lowest values, to red, meaning the hottest values. All right, so that's what this map is. And you know what when I make these kind of maps, I always like to go properties for all symbols. From all symbols. And I like to change the outline color to no color. Yeah, there we go. All right, so now this is a map of the average wintertime temperature in every county in the United States. Well, in the lower 48. I just still don't know where that one. Maybe I'll have to open up. Let's see what the lowest one is. Open the attribute table. Go over to mean. So that's it's up there, but right next to Lake of the Woods. That still seems really, really cold. I wonder if these are multiplied by 10. Yeah, no, they're multiplied by 10 because look, the highest one is 193. So they're multiplied by 10. So that's okay. All right. Still, that's negative 14. I don't want to be hanging out up there in the wintertime. So yeah, it seems reasonable. So we basically need to do this 5 times. How many times? 1, 2, 3, 4, 5, 6 times. So we did it for this one, but we need to do it for these other ones. So if we go back to history, which is in catalog, toolboxes, no, history is right over here. So we've got this zonal statistics table. So you can go back in the history and I can bring up something that I've run before. So I'm going to remove this join. Joins and relates, remove all joins. Catalog, history. Okay, so now that we don't have those dots. So now I can just change average wintertime temperature to average summer temperature and change this to summer temp counties. And everything else could be the same. Run it again. And then I can choose average winter precipitation and say precip winter. Run it again. And I'm basically going to run this 4 times. So this is summer precip. No, 5 times. Because I got to do elevation as well. We got elevation. elevation. All right, so I got elevation. So now I've got all these tables down here. Winter temp counties, summer temp counties, winter precip counties, summer precip counties, and elevation counties. The only one I'm missing here is the predominant land cover. And so the predominant is going to mean the majority, meaning the most often encountered value. So here I'm going to choose current land cover and say LC counties. Actually, I'll just say land cover. And run it. So now once that runs, let's open up that table because it'll be interesting. So this field represents the majority land cover for that county. So I don't know what 20 represents. Maybe it'll tell me if I open up the current land cover attribute table. So 20 represents water. Wow. So I wonder what county that is. So there is a county where the majority land cover is water. So if you zoom in here, you can see that there are some watered areas. And county boundaries do go out into the water. So there probably are several like that. What about 4? There's a whole bunch of counties right here that are 4. 4 is forest. Specifically, needle leaf evergreens. Looks like there's a whole lot of that around here, right? See all these needle leaf evergreens? In fact, our county might be that. All right. So the next thing that we need to do is to put all of these things in the same table, because when we go to run the regression tool, which is actually called OLS, see the ordinary least squares regression to determine the lapse rate by lapse rate using the summer temperature by county for the entire country. So we're going to use ordinary least squares. So using the ordinary least squares regression model, we need to have a single feature class with all of the variables in it. So we need to build that because right now that doesn't exist. We don't have those values. And this is going to seem a little bit monotonous, but sometimes you have to do it like this. So in each of these values, in each of these tables right now, if I open up wintertime counties, the field is called mean. And we need to join the table and then create a new field and then calculate the values into that new field and then unjoin the field. So it would be kind of cool to do this using a model, but since we only need to do it 5 times, it would be a little bit overkill for what we're going to do. But it is something that gets done enough times that it'd almost be nice if there was a tool that did it, or if we wrote a model that would do it, right? So anyway, this is what I'm talking about. This is the workflow. So we're going to go back to our counties, and we're going to say join, and we need to do this several times. We're going to choose the counties, and then the input field's always going to be object ID, and the join table is always going to, not always going to be, that's what's going to change each time. We need to do each one of these tables that we created. So let's start with, let's do it in the same order that's on here. So we'll start with elevation. And then we're going to always use, what happened there? I'm going to open up my elevation. Oh, it's elevation counties. Sorry. Elevation counties. And it's always going to be object ID _1. Okay. So the workflow is we need to do an add join. And once we've done an add join, we need to open up this attribute table. Notice how we have a field now called mean. We need to create a new field, and we're going to call it, I'll call it elevation, or sorry, elevation. I'll call it mean elevation, mean _ elevation. Seems like a good one, and it'll need to be a double. So hit save. Go back here. And then calculate that as the mean. So click on mean. So now that value will go into that other value. And then you can right click on it and say joins and relates, remove all joins. And it should keep that field, and it did. It kept that field called mean elevation in that table. So this is like a fairly common GIS operation of updating a table to have a field that a join table had. So we need to do that several more times. So we'll repeat it again. We go to, well, here we could go to history. So these are the three. Sorry, these are the three. Sorry, no, we've already done all of these. These are the two operations we need to do. Add join, calculate field, then remove the join. So I'm going to add a join. This time I'm going to select, instead of elevation, the next one is winter temperature. Winter temp counties. And that's always going to be the same. So we're going to run this. So now we have this new field called mean. We need to add, there is a third thing. So this will be mean, winter, temp. And we'll also make that a double. Save it. Go back to the counties. Calculate that value as the mean. Oops, that's what we want. Down here. Mean. There it is. I'll run that guy. And then remove the join. So now in our counties table, we have two new fields. We have the mean elevation and the mean wintertime temperature. And we just do that, what, 1, 2, 3, 4 more times. So summer temp counties, everything else is the same, run it. One thing I think we could do to speed this up, maybe, is to add all of the fields at the same time. So we don't have to do that step independent. So make this a double. click here to add a new field. Mean winter precip. I'm just thinking this will make it go a little faster. Mean summer precip. And then the last one is land cover. And that one is, actually leave that as a long because it's an integer number. Okay. So now I'm adding all of these at the same time. Summer, winter, summer, land cover, yep. These are the last 4 that we need to do. 1, 2, 3, 4. Hit save. Okay, so now we don't have to do that each time through, but we do have to pay better attention about which column we're clicking on. So now we've joined the summer temperature this time, and so we need to make sure that we are on summer temperature and we calculate the field and we choose mean. So then we can remove all joins, and we can go back and run the add join again. So now we're just going to be doing add joins and calculating. So we got the summertime temperature, wintertime precip is the next one. Run it to join. Right click on winter precip, calculate field, choose mean, run it. Unjoin. Add the join back. This time it's going to be summer precip. Calculate field. Mean. And the last one is slightly different because we're going to click majority. So right click, or sorry, we need to do the add join first. Choose the land cover counties, run it. And calculate field. This time choose majority. And then remove all joins. So now we have all of those fields, all those, what is it, 6 or 7 fields? 1, 2, 3, 4, 5, 6 fields. So we have all those 6 fields added into our county's data. 1, 2, 3, 4, 5, 6. So now we can do our ordinary least squares regression to determine the lapse rate using summer temperature. So we're trying to find the slope of this model line where each county is an observation. So what's the dependent variable going to be? So the dependent variable is what we're trying to predict. So in this case, it's going to be temperature. We're trying to predict temperature based on the independent variable is elevation. Okay. All right, so let's do that. So we'll go back to geoprocessing, run OLS. We're going to choose counties. The unique ID, it does need a unique ID field, so we can choose object ID. So the output feature class, that's fine. The dependent variable that we're going to choose is the temperature. Trying to predict temperature. There are several temperatures. Let's start with, I said temperature, but I wasn't specific, was I? So yeah, let's choose wintertime temperature. Actually, I think I'll do summertime temperature. And then our explanatory variables, it'll be interesting. We'll eventually put in more of these, but we're definitely going to put in elevation right now. So we're trying to predict, we're trying to see if temperature can be explained, how well temperature can be explained just by elevation. So does elevation explain temperature? I'm going to run that. It's going to take a few seconds. So if we try to do this for every single cell, it would take a lot longer. All right, so here is the strength of that relationship, is the R squared value. Okay. So there's two R squared values here. They're always going to be pretty close together. One's the adjusted R squared, one's the R squared here. It's 0.32, meaning that there's not a very good relationship. That ranges from 0 to 1. So there's not a very good relationship between the elevation and the temperature. Just those two values. Okay, it's not a very strong relationship between these two. So what is the slope, though? Like, the slope, there's the intercept. There's a coefficient, variable coefficient, A. Just looking for the overall make this bigger, see if it formats a little bit better. Yeah, it does format a little bit better. Okay, so this right here is the coefficient for the mean elevation. In other words, I take, for every 1 unit of elevation, which I forgot what units these are in. Let's see if we can tell. So the elevation goes to 4,307. So it's probably meters, right? Because the highest point in the United States is not 4,307 feet, right? It's like over 15,000 feet. So this makes sense. All right. So anyway, for every 1 unit change of elevation, on average, the temperature changes this much. That's what that's saying. So we've used a regression equation to find the lapse rate. In other words, how much that changes. Now, it's not a very good relationship, but that is the relationship between elevation and temperature. Why wouldn't we be able to explain just, why wouldn't we be able to explain temperature just by elevation? What other factors are there involved? I mean, as you go up, it gets colder, right? But I already mentioned that humidity is one of the changes. Yeah, latitude is really important. Now it might, yeah. I mean, latitude is location. Is there anything else that might change it?
Distance to ocean.
Yeah, the water distance to water is definitely correlated with humidity. Like if we didn't have humidity, so let's say that we wanted to use. Let's say we also wanted to include the precipitation, because that also probably correlates with humidity. So let's look at precipitation and see how that changes. Now, why did those get? Anyway, look at. It didn't change it at all. Oh, that's just the next output. So that actually didn't change it very much at all. The R squared is still pretty low, using both elevation and precipitation. Okay, but if we put in other variables, we might see that change. But I didn't actually continue on that model at all. So that is something that we look at in a lot greater detail in the vector analysis class. So that's a course that we take next semester, or that you can take next semester. It's offered. Okay. So we went through all the answers here. Oh, except for this one. What areas are significantly different than the model says they should be, and why do you think they are so different? So ignore this one for a second. Oh, I need to rerun it. Let's take out summertime precip. This map shows you how different it is from average. In other words, that trend line that it created, the counties that follow the trend line most closely have values close to the middle here. And as you get outside, those are significantly different counties. In other words, those are counties that buck the trend. In other words, the elevation change is much different in determining temperature. Okay? So where do those darkest blue and darkest red counties exist? Well, let's start with darkest blue first. So the darkest blue counties are up here in the Pacific Northwest. In other words, it's in those areas, there's a very different relationship between temperature and elevation than there is anywhere else. What do you think? Maybe you're not familiar with this area, but what do you think that relationship? How do you think it's different in those areas?
Because that precipitation is close to the ocean.
It's close to the ocean, and the climate is very moderated by the fact that it's close to the ocean, and so elevation doesn't actually have a lot to do with temperature in those areas. It's cool everywhere, cool and wet everywhere, whether you're high, whether you're low, particularly in really low elevations. Like if you go way up on top of Mount Olympus, it's probably cold. But if you're much below the peak, all the way to the ground, most of the time it's pretty cool. I went camping in this area. We forgot to bring like warm clothes in May, and it was pretty cold. All right. So what about this area right here? In this area, what's going on there?
Yeah, there's precipitation, so the temperature will be much higher.
Yeah, that area is the Mojave and the Sonora Desert, and so there's almost no precipitation, and not only that, there's almost no humidity. And in those areas, the lapse rate is very dependent on. And so it's almost all dependent on how high you are. You go up higher, you get colder. You go lower, you get warmer. Almost without exception in those areas. And so those areas are very much related to elevation.
Dr. Rupert,
Yeah.
for your order least squares calculation, which one did you use for the unique ID field?
I used the object ID. All right. Yeah, I think that we have more time to cover this in in the 417 class. But there are ways to there are different regression tools. One of them is called geographically weighted regression, and this tool is a fairly new technique that actually creates a different regression equation in different geographies. And so if I do the same inputs, the counties, and I make the same, still trying to predict temperature, temperature, trying to predict summertime temperature, and I'm going to leave this blank. So basically, you would choose logistic if you're just trying to predict presence, absence, or yes, no, but we're trying to predict a continuous value, temperature. And also, if you were trying to predict counts, 1, 2, 3, and they were ordinal, then you should, or they were ordinal, select the Poisson distribution there. Okay, so here we're going to select just elevation, and here it's going to basically create those regression equations based on a neighborhood, and we can select those as being a number of neighbors or as a distance band. And so let's just select. Well, I'm gonna just use the defaults, the number of neighbors, and say, I don't even really know what golden search means, but my guess is that means it chooses it on its own. So I'm going to use just the defaults there for now. But when this runs, it's gonna have a much higher R² value. But it's not going to tell us about the overall trend as much. So here's the R² value, 0.9874. So it ended up choosing the 31 nearest neighbors. So it basically created a separate regression equation just for groups of 31 neighbors. And that's why it looks so different. And here you can see on the eastern side of the United States, it did an awesome job at creating models. Okay, but over here there's a lot more breakup. Why do you suppose that is? Well, there's a lot more elevation variety out west, and so I think that's why it didn't do as well out there. But anyway, that's geographically weighted regression. But I didn't even plan on talking about that. We cover these a little bit better in some of the other classes in 417. These are all in this spatial statistics toolbar, modeling spatial relationships, spatial statistics. Now, the one kind of weakness of these is that they don't work in raster GIS. You have to convert everything to vector GIS to actually run these tools. You could convert, you could convert them all to points if you wanted to do that, but you do have to do it that way. Okay. So I think we answered all those questions there. All right, so let's look at the first one. The first exercise, which is, I think, pertains a little bit more to the bulk of the lecture today, is doing a model calibration exercise. And so in our model calibration exercise, what we're going to do is to calibrate a simple model that predicts where kudzu is going to get to. The maximum extent of kudzu. So where's it going to go? Everybody know what kudzu is?
Yeah.
Okay. It's not as common here as it was in other places in the South. Even northern Mississippi, it seems to be a lot more common. But we have a number of layers. I'll go ahead and add those here. I'm just going to create a new map. I'll just use the same project, but I'll create another map in that project. So now I've got my other map, and I will add, you know what, I think let's see. I think I messed up, although I don't think it matters too much. Here, I don't think I, yeah, okay. I'm going to close this map up and just try something real quick. So, do you see where the United States showed up? Is that where the United States is?
Depends on how you look at it. All of our stuff is made there.
Oh, all of our stuff is made in China, right? Right. So, this data, I made it independent of ArcMap, and I evidently didn't save it in the right projection. Let's see what it says. I don't know if I'm going to be able to fix that. It's not really actually that important for what we're doing, but let me just see really quick. So this doesn't overlap. There is a tool called Define Projection. I'm going to see if running it on this helps. So I'm going to choose the US temp 25K, and instead of this user-defined azimuthal equal area projection, I'm going to actually try to see if I was actually using a real one. So if this doesn't work, though, we'll just go back in. So don't try this at home, or don't try this along with me. Okay, so I'm going to choose North America. No, it needs to be projected. So I'm going to projection, continental, North America, Albert's equal area. That's Lambert. We don't even have that. Lambert conformal conic. Yeah, I don't think this is going to work. Okay. What we can do is just actually turn off this topographic map and ignore it. So this data won't overlap with other data, and we could take the right steps to get it into the right projection. But all the internal measurements of area and distance are as accurate as they would be on any normal national scale map. Okay, but we're just gonna utilize this data. So what we need to do is to calibrate a simple capability model, and our model is trying to attempt. I'm gonna put this one up on top. Is trying to attempt to predict this distribution. This is the distribution of kudzu in the United States. So this is a map that somebody made. I should get the right credits to this, but this is a map, and it doesn't necessarily show the intensity. So even where we are, it shows as there being kudzu. I'm sure you could find it if you really look for it, but it isn't as common as it is like kind of right up in the foothills almost is where you get a ton of it. So it has a core, but this is its kind of maximum extent. So we're trying to predict the values in this map. I'm gonna turn these maps off here. We're trying to make a map that looks like this, based on things that we know affect kudzu growth. So here is U.S. temperature, your average annual temperature. Here's average annual precipitation. Here's average annual frost-free days. And here is just a map of the U.S. lower 48 states for reference. Okay, so we have each of those data sets. And what we want to do is we want to be able to come up with a number for precipitation, frost-free temperature, and average annual temperature that will, some linear combination of those numbers will help us to predict this value, okay? So we're going to use kind of a brute force approach. Here's the model that we're going to do. Okay, we're trying to come up with values to explain this distribution. So in order to do that, the first thing that we're going to do is look at the ranges that we should test. So that's what I'm having you do here. So we're going to find out our constraint values to test. So what we're going to do is we're going to find out the minimum values for each of these other data sets. The minimum values for the kudzu, the minimum values for precipitation, for temperature, and frost-free days. Because in each of these cases, we're assuming that there's a certain amount of temperature where if it gets too cold, kudzu won't grow. And there's a certain amount of precipitation where if it gets to, it won't grow. Okay? So how would we find, I don't even know if I should answer the question again because the answer is the same. So we're trying to find the minimum temperature in this zone. So we're going to use zonal statistics as table again. So we're going to try to find the minimum value for the kudzu area. So we got our kudzu, and our zone field is the value. The values of 1 are what we care about. The value raster is going to be, we're going to have to run this on each of the other 3 data sets, temp, precipitation, frost-free. So let's just call this zonal underscore temp. And we want to find what? Min, mean, max, range, standard deviation. What do we want? Minimum. Yep. So keep no data. Keep that clicked. Hit run. And we'll open up the table. Oh, I did zonal statistics, not zonal statistics as table. I can still get the answer right here, right? If I click, everywhere I click inside of zone 1, I'm going to get the same value. So that value is 10.09. And really, I don't think we need to be that precise. So I'm just going to say 10, because we're talking about temperature here. Close that out. So the annual temperature is 10, and this is in Celsius. So in other words, the minimum temperature that kudzu is known to grow in real life is 10 degrees. That's as cold as it gets for kudzu. Otherwise, kudzu dies off, evidently. I mean, there isn't any other area where kudzu exists in a colder temperature. That's what we're trying to say there. That's the logic behind saying it's a constraint. So we need to do that. I'm going to do zonal statistics as table. because it's better. And then choose the kudzu value. Value raster we're going to choose as precipitation. And then we're going to make this zonal precip. And we want just the minimum. Run that guy. Now we're going to get a table. It'll be a little easier to see here. So now we can see in zone 1, the minimum precipitation that any kudzu exists anywhere is 3172. So what that means is that, and this is in millimeters, I think. Annual precipitation in millimeters. So that would be 3.1 meters. Right? No, millimeter. Yeah, 3.1 meters. So that's actually a fair bit of rain. You can see that the minimum value is 124 in the rest of the United States. So there's no kudzu that exists outside of an area that gets lower than 3,172 millimeters of rain. And then finally, now we can just change this to FFD. Change this value to frost and say run. And we'll get a different data set. And you can see that the number of frost-free days is 146. The minimum number of frost-free days is 146. That means that in areas outside, there's no kudzu in areas that receive more than 146 frost-free days. Did we want minimum there? Like, because you think kudzu would be scared away by frost, right? Just for fun, I'm going to hit maximum here and see what happens. 330. No, we don't want that. That's 330 frost-free days. That's the maximum number. Yeah, minimum would mean that we don't get any less than 146 frost-free days. So if that number went down to like 18, that means they only got 18 frost-free days. Yeah, so in this pink-colored area or coral-covered area, there's somewhere there's 18, like up here. There's some area that only gets 18 frost-free days. That's pretty cool. Yeah, I don't know if that's accurate or not. It doesn't really matter. What is important is inside this green area, the minimum number of frost-free days is 146, meaning that there are still over half of the days, not over half. Yeah, over half of the days are frost-free. So yeah, that's right. So these happen to all be constraints. So what we're saying is that it has to be pretty cold, and it has to have an annual temperature of 10, frost-free days of 146. Now, let's see if we make a map just using these three constraints. Let's make a map just using those constraints and see what our map looks like. Okay? Let's do that as a model, because it'll help later. So we're going to do that as a model. And we're going to put these values in first. Okay? So I'm going to do this in Model Builder. First of all, let's talk about this error statistic that we're going to do. We only have two classes. Analysis, Model Builder. I guess I can't do two things at the same time. Model Builder. let's talk about how can we calculate accuracy when we only have two maps. What would be a good way to define accuracy? Let's say we make a map and it shows kudzu like right here. I'm just making up in here. So, like, oh, I can use these things now. If this shows up, even in the recording. Let's say, you have to do something.
It did, for sure.
It did move the thing, but so does this. Well, I guess it's not as cool as I thought. But yeah, you can see this. Let's say that the kudzu area showed up kind of like that, okay? Right, just for fun, right there. How could we mathematically, or using a GIS operation, determine accuracy? So let's think about that. There are two different layers, two different raster layers. If we said the kudzu was right here, is it accurate right here? Why not? If we said that there's kudzu right here, we're saying that there's not kudzu everywhere else, right?
So yes, it is.
It is accurate right there, right? So if we have kudzu right here, what about right here? Is it accurate right there? If we say kudzu is right here, is it accurate right there? No, it's not. Okay? All right. Now what about right there? Is it accurate right there? If we say kudzu is right here? Yes. Is it accurate right there?
No.
No. Okay. So that's correct. So we've basically got a problem where if we did an overlay, anywhere where we say there's kudzu and there is kudzu, we're right. Anywhere where we say there's not kudzu and there's not kudzu, we're right. But the other two problems are wrong. Okay? So we just need a way to mathematically express that, because these are just two rasters. So let's first build the raster that I'm talking about, and then we'll find a way to express accuracy. So in the model builder, here, whoops, I got two models. Okay. Oh, now I've got two models. In the model builder, we're going to have three variables. Then they're each going to be. We're going to keep these to integers. We're not going to get into partial. That's one reason why I did precipitation in millimeters. So we're going to have three variables as our inputs. Long. And they're going to be long. We're going to rename these. And I'll post this. I'll post this model that we build together. Okay, long FFD, and we're going to rename this. Temp for temperature, not temporary. And we're going to rename this precip. Okay. So we've got FFD, temp, and precip. So what we need to do is we need to drag on an operation that will allow us to create a predictive kudzu surface from those areas. Okay. So we could do it as it might be easier to do it as three separate operations and then combine the results of the operations, right? So if it truly is a threshold, then we just need to basically have three. How could we ask what are areas that have an annual precipitation of less than 3172 using a GIS operation, a raster GIS operation. I think there is a raster GIS called less than, right? But we could also do it as raster calculator operation, right? But so this less than operation is a cell by cell basis. In fact, let's kind of look at the help here. It's always helpful. So what this does is it says, okay, if it's less than, you give it the name of a raster and you give it a value, and it outputs either a 1 or a 0 depending on whether or not it's less than. So that seems like it's going to work, because we'll just put in the cross-free date raster and we'll put in the threshold value and we'll get our output raster and it'll be great. So let's see what we can do there. So I'm gonna drag this less than operation onto here. So we could say if the US frost value is less than the frost-free days, then I wonder though, because we actually, do we want, I guess we can always reverse the numbers later, but it's a pain, right? So we're actually looking for the areas that are greater than that value, if you think about it, right? They've got more frost-free days than that, because more frost-free days and more precipitation and how warmer temperature we're assuming are better. So let's actually use greater than. Sorry, less than. Or, I mean, I guess we could use another way to do this, I guess, would be to say, would it work to just say frost-free days? Is that logically going to work? Frost-free days, and then put that there. In other words, what we're saying is the value, is frost-free days less than the value in the raster? Is precipitation less? Might just be easier to use greater than, right?
Might be, but we're still going to get some different numbers, right?
No, the numbers are fine.
That's right.
Yeah, the numbers are fine. It's just because we're looking for the cutoffs.
Right.
Well, let's just run this and see what happens. Okay, I'm just going to call this FFD thresh. I'll call it FFD cutoff. I'm going to run this. Just why isn't it ready to run? Why isn't that ready to run?
But do you have to put a value in there?
A what?
A value.
I put FFD in there. I thought I put, oh, you're saying, do you have to put, oh, yes, thank you. 172. Oh, wait, that's not the right one. I'm on FFD. 146. 146. Thank you, Elvis. Good observation. So let's run that and look at the result and see what it looks like.
Wait, where'd you put that number at?
Right inside of FFD. Okay, so these are the areas that have frost-free days. Let's look at the numbers. So what we want those purple areas to be 1. And that's right, okay. So these are the areas that have frost-free days that are 146 and up. In other words, if we're just looking at frost-free days, these are the areas that we think could support kudzu, because kudzu is supported by having a large number of frost-free days. Now you can see all the way up into Seattle, we're getting frost-free days. But there's other problems with Seattle, and there's other problems with Southern California, namely being there's not enough precipitation in Southern California, and probably the temperature is a little too cold in Seattle. Okay, all right. So let's do those other ones. I'm just going to take this one and remove it. So we've got 3 different less thans to throw on here. So we've got one for temperature. So we'll just go into here, and remember we have to do temperature first, the model variable temperature, and the constant value is going to be the temperature data set. And we'll just call this temp cutoff. And we do have to change the temp value. What was the temperature cutoff that we're going to start with? 10. Somebody said that, I think. And then finally, the last one here is going to be precip, and we'll just call this precip cut off. Okay. And then this is going to be 3.1. This is going to be 3.172. All right. I'm going to auto layout. All right. So now we've got each of our processes. They're each going to create those 1s and 0 maps. And so what we're concerned with is finding the map that meets every single criteria. It's kind of very similar to what I talked about in the Navy example. What we need to do is multiply all these together, because what's 1 times 1 times 1?
1.
Yes. What's 1? If there's any 0 in there, it's going to be 0. It's going to be the minimum value. We could also, there probably is a tool that that'll give us the minimum value of, I think it might be called local statistics. Cell statistics, that's what it's called. Cell statistics, where we could actually put all 3 of these data sets in here and then choose the overlay statistic to be the minimum value. I guess that wouldn't actually be what we wanted either, though, because we want it to always be 1. So we don't want the maximum either, because it has to meet all the criteria. So we really do want to do multiply. It might be interesting, though, like for Dan's example with malaria, he's got 1, 2, 3, and 4. Might be interesting to add them up in some case if we're trying to predict. Yes, thank you. Times. Okay, so we got times. We're going to have to do 2 times, or we could just do a raster calculator expression. Let's just do 2 times. All right. So I did 2 multiplication operations, and I'm going to save this as, I'm just going to call this one kudzu. All right. I don't really care what this one's called. So I'm going to run this whole thing, and we'll see where the kudzu areas are when it's all done. I'm going to add this. All right, so those are the areas that just selecting the minimum areas have created. Now there's some errors, right? There's this area over here. This whole thing looks a little bit different. The whole boundary. Okay. So now what we want to do is what I was trying to describe before. We want to look at this map compared to this map, and we want to come up with a number. We want to be able to come up with a number that represents the overall accuracy between those two data sets. So I got those two numbers. Beep, beep. So how do we do that? How can we compare these two data sets? What if we, for example, what if we multiplied those two data sets together? Could we come up with a measure of accuracy? What would happen if we did that? If we multiplied them together? They're just 0 and 1, so anywhere where either one was 0, we would get 0. So it would kind of tell us the common areas that were both 1s, which we might be able to actually infer the rest of the equation from that, right? Like, would we be able to? No, we wouldn't really be able to, because we wouldn't also know where the common 0 areas were. Right. Okay, so what's another mathematical operation that we might think about? What if we added them together? What would happen? Let's think about that for a second. So if we added them together, what would all the possibilities be in the resultant value, in the resultant data set?
0, 1, and 2.
Yeah, we could get a 0, we could get a 1, and we could get a 2. What would the 0 indicate?
Where it's not at all.
Where one will.
Would they be accurate areas? Or
Accurate areas.
they would be accurate areas, yes. What about the 1s? The 1s would all be not accurate, but they'd be different types of not accurate, right? In some cases, 1s would be correct in reality, but incorrect in the model, and sometimes it'd be incorrect in the model, but not correct. I guess correct is what I would say. 1's in the model, but not. In other words, it's when they're different. But if we're only concerned about overall accuracy, not errors of commission and omission, we're okay, right? We could actually, where's the other accurate places? 2's, right? So 2's are also accurate. So this would work. If we just add them together, then we're going to be able to find out which ones are accurate and which ones are not accurate. Agree? Now, if we actually wanted to find out the type of commission error, if we go way back to the beginning here, we could do something like we could add 10 to one of these values. And so when we overlaid them, we would get 4 different possible values. We get 0s, because 0 plus 0 would still be 0. We get 11, which would be 1 plus 1, which would be, so 11 would be accurate in both places. We'd get 10, which would mean if we added 10 to this layer here, this layer, if we had added 10 to there, 10 would mean that it was a 1 in the kudzu area, but it was a 0 in real life, meaning that we over-predicted. And then a value of 1, or sorry, yeah, a value of 1 would mean that it was on the other side of that flip-flop. But we don't really need to do that, because we just want to get an overall accuracy statistic. And so we can just do plus. Let's go back to our model and do plus. That's what it's called. We'll throw plus down there. Notice that I'm always pulling the spatial analyst licensed one on there. They all do the exact same thing. It's just that this is actually asking your computer for a spatial analyst license, image analyst license, or a 3D analyst license when it runs. Okay, so we want to add the kudzu areas, and then we're always going to add the US kudzu 25K. It's always going to be that one. So this one's going to be the, I'll call this, we're going to have to massage it a little bit, but that's going to be one of the accuracy data sets. Okay. All right, now if we really want to find out the total number correct versus incorrect, really we'll need to do the zeros, the ones, and the twos. Let's look at what this looks like first. I'm going to run this guy. Can I run just this guy since the other part's already run? Yeah. Okay. And then I have that. All right. So now we have those three colors. So everywhere where it's purple on this map is what? It's wrong. It's incorrect. And everywhere where it's either brown or blue, it's correct. If we look at the attribute table, now why does it have an attribute table? Yes, there are three possible values, and because there aren't an excessive number of possible values, it I forgot that I should probably be putting this around my neck if I'm going to walk around. Okay, so if we want to, we could find out the overall accuracy. Looking at this table, we could take 8251, 2652, add those together. That's the total number of correct. And then we would just add that we would just add all of the numbers together, and that would be the total number of cells. So I'll show you what I mean real quick. I think I can, yeah. Let's just do it in Excel here. Oops. So if we take this number plus this number, and then we take the sum equals the sum of all three numbers. This divided by this. So the overall accuracy of this map is 89%. So 89% of our cells are classified correctly in this map. Now I think we can do better, but that's just using the minimum values. So how could we do better? Well, if we adjust the values to be different, we can get a different result here. So like what I'm talking about is, let's go back into our model here and go back and choose a different value, let's say for frost-free days. I'm going to choose a fairly significantly different value, 150. Now I'm going to run the whole thing and see what we get. It's going to take a few seconds here. Okay, so now here's our new map, and we can look and see what that did. Oh, it didn't do a whole lot. It's about the same accuracy, right? Or yeah, These numbers are still updating. Yes. Yep. So it didn't change it a whole lot, but it did change it. It's those numbers are different. Let me make sure they are. Okay. Yeah. Okay. Did we get better or worse? We really didn't get anything different, right? I mean, the number was almost identical. 89.09 versus 89.09. Yeah, it's really, really similar. 89.04 versus 89.09. So it got slightly more accurate, but not very much at all. Okay. But that's the idea here, is that we can adjust those input parameters into our model and see how each of them interacts with the other one to produce a map. And so we could do we could check out different values. So if you look in lab 10, sorry. Actually, did I did not include the values that I wanted you to test over, did I? Is there a table anywhere in the oh yeah, no, there is. Sorry. I added it to it. It's right here. No. Let me go back to map 1, add data. Oh no, that's the output table. Yeah, so this is showing you, this was just meant to show you we already talked about this, but this is meant to show you that the zeros meant that no kudzu was correct, 1 is incorrect, and 2 is kudzu's there and it's correct. Okay, that's what each of those numbers means in the output table. Okay, so anyway, I have a set of values that I wanted you to test over. So I got to upload that. But what we're trying to do is find the best possible value. And so you're basically gonna have to check three different values for each one. So that's 3 times 3 times 3. What is that? 27 different times you got to run the model. Now, it would be helpful to be able to create a way to automatically output a number, right? To store in terms of the accuracy, right? So let's, yeah.
There's a way you can run it 27 times with formula instead of formula do that, and you got to stop with 27.
Right. Well, you can do the same way we did the temporal one, where the only way I have successfully been able to do it is to make this a model, save that model, and then put the iterator in a different model and put the other data set inside of that one. Remember how we did that in temporal modeling? We tried to do the iterator in the model, and I can never figure out how to do that in ArcGIS Pro. Doesn't work well. So you take this model, you save it, and you run it. So, but in order to do that, you really need to do this last step that I'm talking about, is that it would help to be able to spit out a number at the end, right? Not just spitting out, like, there's no number here, is there?
Like June, July, August, September, stuff like
Well, this isn't June, July, August, and September. This is like a % accuracy using these inputs. See what I'm saying? Right. And so otherwise, you have to run it 27 times and copy the values in 27 times, which, you know, it isn't horrible, but you're right, it isn't like it isn't super fun. So how do we do that? Well, I haven't found a really good solution for doing that myself. But yeah.
How you pull up the number 27?
Am I doing the right number? So I'm sorry, I don't have I forgot to include the table that you need to test on. But 3 times 3 times 3 is equal to 27. Yeah, it's 27. So I have you test 3 different FFD values, 3 different frost values, and 3 different precipitation values. Now, in reality, you would definitely want to test much more values and set it up as an iterator. But like I said, I haven't found a way to do this that's really clean without scripting. So I usually do it in scripting, but I'm sure there is a better way to do that. What we need to do is remember that this contains an output table. And so there are these utilities that allow you to calculate a value. So this returns a value based on a specified Python expression. Okay. So let's see what the inputs are. Expression. Because what we need to do somehow is take this attribute table, and there's always the same number of cells. So actually, we really only need this number, if you think about it, right? Because as long as we know how many cells there are, that number, we're going to be able to do 1 minus that number. So 1 minus the number of cells. I'm trying to think here for a second of a convenient way to do this. So what if we selected out that row and then added that row to a table that was that we created beforehand, and copied it into that? I wonder if there's, for those of you who've taken a GIS class before, you think there's a tool that will append? Yeah, there's a tool that does that. Append. What does append do? Append. Let's see if this does what we want it to do. So appends multiple input data sets into an existing target data set. Can be tables. Okay. So this is my idea right here. So what we do is we select out just this row into a new table. And to do that, we also need to find out how many cells there are overall, because it's always going to be the same. So we select just that row out. Then we put it in a table, and that table has a field called overall accuracy. And then as a next step, we calculate out in that field, we calculate the overall accuracy from knowing this and the total number of cells. Does that make sense? And then Well, as it runs through, it will always have the rows in it. In fact, what would be even better, this will be even cooler, we will in that table, it will also have the number of frost-free days. It'll basically have these values in it. Okay, so this is the way I think we should implement that. Let's actually do it. Let's do it once manually. What kind of manually? Okay, close this. So the first thing that we need to do is we need to, I think it would work best to select that row. So there is a tool called Select, Table Select, selects records, matching a structured query expression. Yeah, that's what we want. So this table is going to go in there. And the expression that we want to do is actually going to be, it's always going to be value is equal to 1. Right? So what we're doing there is whatever gets into this accuracy table, we're going to calculate just the row that has the value equal to 1. Why? Yes, it has the number of incorrect values. Exactly. So we say OK. And so now we have the number of incorrect values in there. So we'll call, what's that?
Can you show the tool again?
Yeah.
It's kind of hard to see on this projector.
Yeah, I can see that. I mean, can't see that. Yeah. I'm actually going to change the name of this anyway. I'm going to call this, I'll call this T accuracy. I'll call it the CACC table. Stands for temporary accuracy table. It's just going to have one line in it. Okay, and then I'm going to hit OK here. And then I'm going to add some fields. I'm going to add 3 different fields. I'm going to add 4 fields, sorry. The 4 fields I'm going to add, let's put them on the thing. I'm going to add 1, 2, 3, 4, and I gotta hook them all together. So the first field I'm going to add is going to be called FFD, and it's going to be a long integer. Yeah, it's going to be a long integer. That's all I'm going to change there is the field name. Then I'm going to change I'm going to make the second field, I'm going to call it temp for temperature. It's also going to be a large integer. So I'm just chaining these together. And I'm going to call this precip. So what it's going to do is it's going to take this table and it's going to add a field called temperature. It's going to add a field called precip, and it's going to add a field called FFD, and finally it's going to add a field called accuracy, and that one I am going to make accuracy. I am going to make that a double. So now it's going to go through, it's going to create all those 4 fields. These 3 fields are just for holding the value in the value that was in these input parameters. You might see the utility of that later in a second. Let's do another auto layout, fit to window. Whoop, now it's getting really long. That's crazy. I'm going to zoom in. So now I've got to calculate the value in each of those fields. So I'll just do that right underneath it. So I'm going to do 4 calculate values. Calculate fields. So I'm going to pull 4 of those on. 1, 2, 3, 4. So I got 4 calculate fields. So the first one I'm going to say, okay, it's going to be the FFD field. Oh, the input table. Here, let's first connect it. So it's going to be the same input table here. Okay. But then the field name is going to be FFD, and the expression, this expression is going to be percent FFD percent. And what it's going to do then is get the value in this FFD circle. So here, I'll open that back up for a second. So that's what you want there. And then we need to just do that several more times. So let's do that again. So the input, well, let's just grab all these and do the same thing. Oops, like this. These are always going to be just chained together because it's always going to be the same input table. So now we go through each of these. This time we'll say that the field is going to be temp, and we'll say percent temp percent. So again, what it's doing when we use this percent, name of a variable percent, is it's pulling that value out of the variable and storing it right there. It is a little snippet of Python, but it allows us to not to have to do a full Python script. Precip, percent. So what I changed here was precip and percent precip percent. And then finally, this one's a little different. This is accuracy. So we need to select accuracy, but we need to think about how we're going to calculate accuracy. It's going to be based on this count field, remember? But like I said, it's going to be 1 minus count divided by something. What's here? The total number of cells. Now, this is kind of a weakness that we have to hard code that in, but for a particular model, that'll always be the same. Let's get the total here. That's the total number of cells. The total number of cells is always going to be that. So it's 1, 2, 2, 3, 8. So what we're doing is we're saying the overall accuracy is 1 minus the proportion of incorrect divided by the total number of cells. So that's the overall accuracy. I'll leave that up there for a few seconds. So now, if we test this, we should now have a new table that has just one line in it. And that one line should be the overall accuracy. So now running this 27 times shouldn't be too much of a pill. Well, one more step is to save this into a table. We'll talk about that in a second. Let's see if this works. Save this into a separate table. Let's see if it worked. I gotta add that table. There it is. So that worked. So see, we've got the FFD, the temp, the precipitation, and then there's the count of incorrect cells, and then here's the accuracy. So now every time we run this, if we change these input parameters, then we'll get a different accuracy result, and we'll just be able to run it over and over again. But it will always be saving it in the same place. So what I'm trying to say is, let's go ahead and save this table as kind of like the master table, and we'll always append to this table. So what I'm going to do is right-click on the table here and say data export table, and we'll put this table in the working directory here, and we'll just call it master table. Yeah, we'll run that, and if we want to, we can even see if we can delete that row. So now, right now, it's an empty table, and what we can do is always add to the master table our results. So how do we do that? Well, that was that thing I was looking up before called append. Yeah.
My final table in the attribute table, temp and precipitation accuracy are null. Why would that be? Like it ran one of the calculate fields?
It ran FFD.
Yeah.
Now, when it ran, did it actually run that step?
It highlighted the calculate field in red, or it looks red, like something went wrong, but it gave me that, like the output. I don't know.
Yeah, if it's red, it probably didn't run. It probably stopped there and didn't go on. What is it? Does it have any red text?
Not that I've seen.
Okay. Well, yeah, I wish I could come look at it. If you want to send me the model, like send me the model, then I can take a look at it. But I will post this model too, so you'll have that. Okay, so the final step here is this append, and what we're going to do is we're going to input. Well, let's input this, and we'll append it onto the. I'll go find it. Refresh. It's called master table. Where did it put it? I thought I put it right there. Oh, maybe I got to refresh. It's one thing I don't like about ArcGIS Pro as much. See master table anywhere? It should be. I don't even see it in this master table right there. Okay. So now it's a master table. One last thing I'm going to do is make each of these inputs model parameters. So precipitation, make it a parameter, make that a parameter, make this a parameter, and then save this. I should have been saving it all along. So now it should be toolboxes, maybe under catalog, project, toolboxes. So here's this one I never ended up using. Yeah. Okay, so here's the model. So let's see if I can run it from here or if I get some errors. But let's go up to 390 and temperature 15. And we'll leave FFD there. Run that guy. I wonder if having everything open will be a problem, but who knows. So it's running through. ArcGIS Pro is a lot better at ArcMap. It did fail though. So let's see where it failed. Table does not meet the schema of the target master table. So what it's saying is that that it has a different set of values. So let's look. See where it put it in TACC table. Let's add that. Let's go to map, add data. Well, I didn't run it in the model. So I think that's the problem. Let me run it from the model builder and see if that still works. So I'm going to adjust, leave that the same, adjust this to 3190, run it, and then run the whole thing. I think, okay. Wow.
Are those numbers outside the range, or I changing those numbers to break the error?
No, they shouldn't. Close that out. Okay. I shouldn't have called this regression. I should have called it calibration and regression. Okay. I'm just going to try running it again. That, to me, that sounds like a call ESRI. That seems like a made up error that that happened because ArcGIS FFD :1. Which, yeah.
What expression did you run in append, or did you run through?
No expression in append. Right here. Yeah, there's nothing in, because I'm just putting it on the bottom. Yeah, I mean that's interesting. My guess is this should match. Okay. Okay, I'm gonna run this thing again, see where it fails. It's creating that, creating the temperature cutoff, creating the next one. Yeah, I may just have needed to validate the whole thing, which actually one of the things validate does is clear out all the memory, the temporary data sets. Okay, so I am having that problem on the last data sets still. Let's add this to the view. So if I add that to the view, I get a value, and that should work. But for some reason, this isn't going into that, and it looks like it's because it has this this row ID field. I don't think I can get away with deleting that field. Let's see. Cannot be deleted. Okay. Where's this being saved? See how this field right here, so a table schema is the definition of the table rows and their data types. And so what it's saying is this schema is different than this schema because I have this row ID field in it. And so I don't know how, well, where, that field didn't get created. Where's this one saved? Just want to see where it is. Source. It's in the same directory. I'm going to run copy instead of copy. Not a data element. So, master. Okay, cool. So you see how this one didn't create, I don't know why when you do copy rows, it does that, but I just used this other generic copy tool to do it. So now I'm gonna delete that puppy. Actually, I don't think I really need to delete it. I can still append onto it. But what I am going to do is change this, instead of master table, it's going to be master. And then I'll just get rid of master table. In fact, I can get rid of it even in the catalog, just so I don't get confused later. Master. Ooh, it's not even there. It must have saved it somewhere else. Anyway, it must have put that somewhere else because it makes me think it did, because that's, why else would it create a different row like that? So now I can run this again and go up. Well, here I'll go up to 15 here and say okay, and then run the whole thing. Now I can't get an exclusive schema lock.
Is it because your tables are open?
I'm going to try to do that. But these are all open as well. Let's try running this toolbox here. So 15. Did I open it somewhere else? Just when I told everybody that you were better at this, ArcGIS Pro. Okay. So anyway, it's not allowing me to edit, to overwrite something. So I'm just gonna, because it says I'm using it. So I'm going to rerun it, but after I restart ArcGIS. There we go. Now it's working. So now we should see a second row in the table, except for I didn't change. Now this time, I still didn't change anything. So I wonder if every single time I run it, it's going to force me to reopen ArcGIS. If that is the case, then what I need to do is change all of those values to be temporary in between. But let's see if it worked. So master, open. Now there are 2 rows. I'm gonna go ahead and delete this row. There are 2 rows. Oh, it did go to 10. So the accuracy actually went down by changing that value. So I should go find out what the values I had to test. Okay. Let's see if it'll actually let me run this multiple times. Nope. Same thing. It's the exclusive schema lock. So that failed right on the first one, the FFD cutoff. So maybe if I just delete all these layers, let's see if it lets me do it then. Nope. Okay. So if I want to make this so that I don't have to do that, because that is really annoying, then usually after, we did this on the temporal modeling script as well. Usually the best way to do this is to modify these, sorry, not these, yeah, these, is to modify these outputs to be temporary. So instead of being this FFD cutoff, you could say in underscore memory, FFD cutoff, and then this would be in underscore memory, and then this one would also have to be in memory. Let's see if it at least gets that to a better spot. I think it's still going to fail. Oh, yeah. So it ran those, but now it failed on this one. So this will work. I'm just going to copy this whole thing, say OK. We did it here already, right? Yeah. So do it right here. And this, I think, is the last one we need to do. But that one we kind of needed to just write over it each time. So hopefully that'll still work. So save, run. That's really strange. It's not even letting me do in memory. What's that?
You don't have in memory on the output rest.
I do on the output. Yeah, I don't really like that either. How now in ArcGIS it makes you click on it to see the full path. Hmm. Maybe we need to do that. It's still saying that it's a it's still saying that it's not it's not allowing me to overwrite that. Oh, that's FFD cutoff. TACC table. It's this one. Table select. Underscore percent FFD percent. Can you do the inline expressions like that? Percent temp percent precip percent. I don't know if that's going to work. It did work though, so look at that. I mean, it worked to do those three. Table is being edited, but it did name it the right thing. FFD. So table is being edited, failed to add field. So where that died right there. That was the first add field. Hmm. I'm not really sure what that means. All right, well, this is kind of frustrating because it's basically making us close. I'm trying to find a way for it not to have to close ArcMap down and open it back up in order for it to run at each step. The model does produce the results that we want. So if I change this back to the way I had it before, where this was just ACC table, and I say OK, and I close.
Dr. Ray, so we stop on where we make that error input and then just lead on from there, just leave it up here.
Yeah, for sure. Yeah, so it would be a pain to have to open it up 27 times, but I'll try to fix that, and then we can look at that, because this should work. Like if I just run this again using, like, let's say 12 now. Oops. 12. Let's just see if this works. Validate, run. Yep. And there's the next row. It does work on a fresh copy every time. And you see how much faster it runs in memory? so it's not saving it out every time to disk. It runs really, really quick. And so it's kind of a bummer that you have to open it up and close it up. There's got to be a better way to do that. But yeah. So we did discover a way to do this. And look, the error went up pretty I mean, the overall accuracy went up pretty significantly. So we're at 92. Okay. So once we figured this out so that you didn't have to open and close it up every time you wanted to run it, we could test all those 27 variables, and you could do that. This is what I was trying to say. You would create a new model, and then you would drag on, like we did last time, drag on model onto model 1, and then you can create a variable from each of the parameters, and then you could modify those each time through the iteration loop. The way that I actually implemented this in a script was that I used an iterator called iterate row selection. So what it did was I actually built a table that had all 27 values. And so what it does is it goes through each row and selects out that table, and then it runs the calculate values tool to pull out one of those values from the table. But that's how I would suggest doing it. But we're gonna end there for now. And so you're just responsible for running this model those 27 times and finding out which one is the of those has the highest accuracy. So I'll put this up there, just like on the temporal model. You might have to change the paths to match your paths, but it should work. And bonus points if you get it to work without having to shut it down. And I'll try it too, because that doesn't make a whole lot of sense. So I had this working in ArcMap the last time I taught this course, and so I kind of expected it to work in ArcGIS Pro. So I don't know exactly what's causing this error to occur, because we did it before on the temporal model. We looped through and we produced similar. We produced the same sort of results. But yeah, if I 3185, if I run this again, I'm sure it's going to just fail again. Okay, now it's not failing. Maybe if you talk a lot in between, it works. So that one 9924661. It's a little bit lower accuracy, but it seems like so far the most sensitivity to accuracy has been on temperature. So maybe, I really don't know, but let's try it. Let's go down to 11. It seemed to make the most improvements. See, this is the way it should work, and I don't know why it didn't work that way before. Because we didn't do anything different, did we?
You're too fast for me, so you might be too fast for me.
So that went down a little bit. So if we go to 13, let's see what happens. It failed somewhere. No, it didn't fail. It just hasn't. Wait. Okay, so that actually went down. So 12 was the best score so far there. And then let's see if we, the temperature, no, the FFD, maybe change that back to like, well, let's just go extremely the other direction and see how that affects it. I'm keep pushing my luck here. Okay, it seems to be working. So that value 9245. So that's still, this is still more accurate. But maybe we kind of went over a hump, because there's basically, if we plotted this, there'd be like humps of accuracy. So let's go back to 155. I'll run that guy.
So you think the wrong combination of numbers can make it crash?
I don't think the wrong combination of numbers can make it crash. No, sorry. 92.433. That's still lower, right, than the best one. Let's see, 9247 is still the best. So let's tweak 390. Yeah. Well, anyway, the ones that I tested kind of converge a little bit better, but I forgot what those were off the top of my head. But I'm testing in the right range, because it was a range of like 20 for precipitation and a range of 10 for FFD, and you're going through 3 steps, 10, 20, 30, and then temp. All right. So for any one of these, if we wanted to actually see this one, we'd have to like run it again to see that result. Yeah, I'm really puzzled as to why 9244, that's still not as accurate as that. I mean, they're all really, really close. 155. .92.5, that's even more accurate. So 146.12, 1390 is the best result we've gotten so far, and we could. We don't need this anymore. We could actually manually add that into the map, because it's the most current result. So we could actually look at it if we wanted to. So that would be, what do we call that? ACC something, ACC1. So that's what it looks like. Whoa. That can't be right? What's that? Yeah, because that's not right, because it would have been 907. Oh, I made them all temporary. So this is like the last one that I ran earlier. Of course, I did run it from here, so I should be able to add that temporary result. As long as I don't rerun it, I should be able to see that one right there. Add to display. Maybe it doesn't. Maybe if I just reran it. It still didn't add it to the display. We'll just create another line in there. Yeah, so I would have to just like rerun it manually, I guess, because it didn't show it up. I think what I might want to do here is, instead of making this in memory, just make this, like I said before, underscore percent FFD percent underscore percent temp percent underscore. So just this one wouldn't be precip percent. This one won't be temporary. Let's make sure it's saving that in the right place. Yep. I wonder if that's just too long of a name or something. Anyway. That's another contact ASRI error, isn't it? Anyway, I think this is the one I'll put up because we know it works. And you could always go back and create it manually. All right, well, it looks like once you get an error that you screw it up. So maybe that's just it, is that I had an error in my script somewhere, and once you do that, when it runs partially through, I could see that. It runs partially through, it gets to an error, and then it won't complete it after that because it thinks that it's still being used because it died during the processing. I don't think that's a good excuse for ArcGIS, but I could see it happening. Is that it's basically not handling the fact that it failed gracefully. It's leaving a process running on your data. So let's see if this works. Yep. Okay. So that I think that's it. So the issue here is that when it fails, for some reason in this process, one of these processes that runs, when it fails, it locks up that data set and doesn't let it be reprocessed. And so there might be a better way to handle it, but it looks like the only way I could figure out is to open it and close it, which that's a drawback. But anyway, it's working now, and I'll go ahead and post this along with the 3 different values that you need to test. So really, you need to test all 3 ranges of values, and I have an actual table that has all 27 values that you need to check. So you could just run each of those and get a result. Okay. All right. Let's see what the yeah. I just didn't post that table. I meant I reference it, but I didn't post that. So you need to turn in the table showing the % accuracy for each of the tests with the lowest error highlighted. Okay. All right. All right. This is going longer than I thought. So let's look at the final review sheet here real quick, and then we'll be done. Okay. So I actually have the final. I already created it, and I created this review sheet from the final that I've already created. And Ashley, will you be able to proctor that? Are you still there, Ashley? Yeah. Will you be able to proctor that on Thursday at what was the time? 10:30?
10:15, yeah.
10:15. Okay. Good. All right. So. Yes. Yeah, I'll send both of the tests to you tomorrow.
Okay. Awesome.
So this will be largely the same format. I will say that this one has a few more multiple choice-esque type questions. They're not completely multiple choice, but they're more, I would call them more like matching, where I give you a few possible answers and then there's 3 or 4 that draw from the list of possible answers. Okay, so it has a little bit more of that. So some people might find that easier, but there's still a fair bit of a short answer that we did before. And you might have to work out a few little problems similar to before, where you're going to have to do it to diagram certain processes. I'll just go ahead and tell you that it's a temporal modeling process that you're going to have to document. And it's very similar to the one we did in the lab. There's just slightly different capability tools that you need to run. So maybe, instead of adding something, you would, but the loop part is the same. Okay, so go back and study that. So this is very heavily weighted toward the second half of the course, but as I mentioned last Thursday when I was on the coast, I don't know if you all heard it here, is that there are still some basic raster operation type questions, and there's a conditional operator that you're given a grid and you have to do a conditional operation, because I think it's really key. I mean, in some ways, if you finish this class and you do what a conditional operator did and what zonal statistics did, then you could do a lot of stuff with just those two things. Those are really important. There's lots of, as Dan said, that's the answer a lot of the time. One of those two operations, because they form some of the basics of logic. All right. So one of them is conditional. There actually isn't one on zonal statistics. The other one has to do with which way water would flow. Okay. But be prepared for a few different questions regarding that. But that's really the only repeat from the last exam. Spatial interpolation is hit fairly hard on the exam. I mean, it was one of the bigger lectures that we had, and so there are a number of questions on that concept. So you should be able to categorize the spatial interpolation algorithms that we talked about into whether or not they're global versus local. And as a hint, we really only talked about one global, which was the trend surface. Most of them are local in that they take the surrounding values and they use just the surrounding values to predict the unknown location. All spatial interpolators, their goal is to predict the values on an evenly spaced grid based on known values at other locations. Okay. So we talked about a few different types. So almost all of them are local. Exact versus inexact. Related concept, but an exact interpolator will predict at a known location, in other words, where you have a known value, a reference value, whether you're trying to predict elevation or precipitation, it'll predict the value of that known location for that location. It won't smooth it. And so that's what exact means versus inexact. Okay. So it just so happens the trend surface is also an inexact interpolator, but they're not all. There's actually a few other examples that are inexact versus exact. But IDW is an exact interpolator. At the location where you have a known value, it will be that value because what it's doing is it's weighting by distance. And so if that distance gets to be 0, it will weight that one so much that it will be the value at that location. Okay. Now, in the lab, we calculated inverse distance weighting in the lab. We talked about that, and so there is one example on the test where you have to calculate IDW. Okay. It's just 3 points though. So go back and review that. Know in general how each of these interpolators operates. So in other words, you don't need to know the formula except for inverse distance weighting. So you need to know basically how nearest neighbor works. That's the easiest one. So nearest neighbor means that for every cell in the output raster acquires the value of the known location that's closest to it. So sometimes it's referred to as Thiessen polygons because it creates these polygon-shaped features because all the values are just the closest known value. Okay, a trend surface tries to fit either a plane or a one-dimensional polynomial, sorry, a first-order polynomial or a second-order polynomial through all of the data points. That's what a trend surface does. So it tries to fit either a plane or a smooth undulating surface through all the data points. That's a trend surface. A spline is kind of related. It tries to fit a bunch of smooth trend surfaces, local trend surfaces through the data points. Okay? It's the best way to think about it is what we talked about in class, is that it's like a rubber sheet that's going through all of the points. Okay, and you can adjust basically how much tension there is in that rubber sheet. So if there's not a lot of tension, then it'll go through all the points and it'll be kind of jagged. If there's a lot of tension, it'll create smooth arcs through the points. That's spline. IDW stands for inverse distance weighting. That one is basically kind of like calculating the weighted average on a test, except for you're weighting by distance, inverse distance technically. Okay. All right, now we did talk about Kriging. We spent a fair bit of time on that. There was a lot of slides that lecture. You don't need to know everything about Kriging, but you should understand that Kriging is a geostatistical method for interpolation that utilizes the general trend and local variability. And you should be able to recognize a semivariogram. So there's a semivariogram on the test, and the parts of the semivariogram you don't need to understand, except for you need to understand the range on the semivariogram and what it means. Basically what it means is that beyond the range, there's no more spatial autocorrelation. And so it doesn't do any good to use it as part of the interpolation. It doesn't do any good to use a point beyond that range to predict any individual value. Okay. All right. So I don't know if we did. Yeah, we're doing this in the right order. So we also had the diffusion modeling problems. We need to know some diffusion modeling terms. So we talked about expansion versus relocation. The difference there. Expansion means that it expands out and it stays in the place that it starts. And relocation means that it moves to another area. And what we did in this class was basically expansion. We modeled more expansion diffusion modeling rather than relocation. All right, you should be able to recognize a capability suitability modeling problem. I know that was from the earlier part of the class, but it's important because it's part of the diffusion modeling. It was also part of what we talked about today. And then least cost distance modeling. Actually, I don't think there is anything about least cost distance modeling on the test. I'm pretty sure there's not. But they're definitely actually, okay, sorry. The only thing that's in there about least cost distance modeling is that you need to understand that there's a step inside of the temporal modeling where you need to use least cost distance modeling. Okay, so that's the only part that's in there. I was wrong. There's no test question specifically on that, but you do have to, as I say up here, you do have to diagram like a temporal modeling process. Okay, so you should remember to loop over each time step, and you should understand the feedback loop. Okay, so that's the one you'll diagram. You also have a test question on the importance of choosing a proper time step. Basically, you need to choose a time step that will allow your phenomenon to at least travel through one cell during the time step. Otherwise, your model will never change, and that's why. So you need to know that concept. All right. And then today we talked about calibration, verification, and validation, so you should know what each term means. And then we talked about acceptability, talked about accuracy. Here you should be able to, you should understand how to calculate percent accuracy. So percent accuracy is on a map. It's the number of things, the number of reference data that were mapped correctly divided by the total number of reference points. When I say reference points, what I mean is ground truth or field data. It's the number of those locations that were correct divided by the total number of those locations. Typically, we should say reference data most often. I know I struggled with it a little bit in the lecture, always saying that, but not ground truth. It's the number of reference points that were correct divided by the number of total reference points. That's the one that we calculated during the lab. We just actually did it the opposite. That's why I did 1 minus, because we did the number that were incorrect divided by the total number, and that gave us the opposite of, not the opposite, but it's 1 minus the overall accuracy. There's no question in this class for this test, I don't think, about RMSE, but RMSE would be the way we would do it on a continuous scale. What is parameterization? Parameterization is the process by which we find out what the inputs to our model should be. Okay, we could do that through regression, but we did it in this lab mostly through just kind of brute force, like guessing and getting feedback. And you could do that if your model runs fairly quickly. Okay. All right. So remember that calibration and validation are 2 different things, and that typically we need a different set of data. So in our model, we only really calibrated it. And so if we had another area in the world where kudzu had been released, then we might use those same parameters to test the accuracy in a different location, right? So typically you can do validation through withholding, having a separate set of data just for validation purposes. You don't want to use the same data to validate that you use to calibrate. Sometimes you can withhold that through having some area that's blind, that's not part of your data, and maybe do it over and over and over again, throw out one sample and test the accuracy at that sampled location and find the overall accuracy. And then we talked about the steps for verification. Basically, you should know that you want to run your model and test each of the intermediate steps and work them out by hand sometimes, or at least verify them by hand. I guess you don't necessarily, I'm not talking about, get out your slide rule or anything. What I'm talking about is making sure that each step works. Oftentimes that's done as part of the building of the model. Like you probably noticed when we built our model today that I would run, and when I've done it every other class where we've built a model, I would run it a little bit as we were going along and kind of look at the results. And that's a very important step in verification, is to understand what it's doing and making sure that it's doing the right thing, because you can be surprised. You think that it's going to do what you think it's going to do, and at the end you get a result and you're like, well, here's my result, and it might even look reasonable, but if you go back, there's like some rounding that it did, or something that you don't know about, and it's not producing what you'd expect. Or you pass it off to somebody and they try running it and it's never changing. It's always producing the same result no matter what the inputs are. Well, somewhere you messed up along the way. So it's important to verify it and then run it a few times to make sure that it works. All right, I think that's it. This test is shorter. We had less, we had less material that we covered the second half of the course. One reason is that we messed up. Well, we didn't mess up, but the weather messed us up for 2 weeks, so we skipped a lecture, and then we had some technology snafus, as I said. This was the worst semester for that. But this test is shorter. I would expect that most of you would finish in way under the 3 hours that are allotted, but you have all 3 hours. Okay. It's similar in length though, but it's a little bit shorter. All right. Any questions? Alice. All right. I'll post those 2 things shortly. I'm gonna upload the lecture first. Let me do that. Stop that recording. Unless there are any other questions,